Hi, welcome to this webinar on Power Hardware in the Loop. My name is Carlos Villegas, and I'm the Electrification Industry Manager at Speedco, where I look after real-time solutions for power electronics, motor control, battery systems, and power systems.
Well, and my name is Gernot Schraberger. I work at the MathWorks as Principal Application Engineer, and my special focus is on physical modeling, control design, and from the application point of view, I work a lot with electrification projects.
In this webinar, Gernot and I aim to provide an overview of how to test electrical equipment with Power Hardware in the Loop, or Power Hill for short. We'll start describing the challenges when testing electrical equipment to highlight why you should use Power Hill. After defining Power Hardware in the Loop and its differences with Hardware in the Loop testing, we'll provide more details on the three main components of a Power Hill test bench: the real-time hardware, power amplifiers and sensors, and the electrical simulations. We'll conclude with a hardware demonstration by testing a grid-tied inverter. We'll be connecting it to a virtual grid using a 60 kVA power amplifier as part of a Power Hill test bench. So Gernot, could you tell us our key takeaways for today?
Yes, Carlos. Our main points for today are first, that you can use Simulink and Power Hardware in the Loop testing to de-risk the integration of power systems and power electronic equipment. Second, that you can test the integration of both DC or AC power grid components with a large and detailed grid simulation. This simulation can be based in SimSkip Electrical and thus enable a straightforward transition from desktop simulation to testing with real hardware. And third, that you can use Power Hardware in the Loop simulation to thoroughly test power equipment like inverters, protection relays, and battery chargers using Power Hill and Speedcode hardware. The nice thing here is, well, you can debug, test, and automate from within the Simulink environment. But first, Carlos, what is Power Hardware in the Loop actually? I'm quite familiar with using hardware in the loop for testing embedded controllers, but not so much with Power Hardware in the Loop. Could you tell us what it is and why should we use it?
Sure, Gernot. But before defining what is Power Hardware in the Loop testing, I think it would help if we first try to answer why we should use it by providing a few examples of electrical equipment testing. There are several challenges to overcome when testing electrical equipment, especially as the full electric system is rarely available for testing and may have safety and cost implications. For example, you just cannot stop the electric grid for doing integration tests. Let's say that you are designing a power converter for a wind turbine, and you aim to have grid-forming capabilities in order to support grid stability. Your power converter has power flow interfaces, typically with a three-phase generator on one side and a transformer connecting to the grid on the other. You would like to test the converter under typical and extreme wind conditions as well as grid compliance. We would also like to test safely. PowerHill provides a safe laboratory test bench for fault testing, and with capabilities for both grid and electric motor emulation, it is used to accelerate the certification and on-site commissioning of full wind turbine nacelles. It can provide a virtual grid, as testing directly with the actual power grid is rarely an option due to the certification requirement, access cost, and the potential to affect other grid users. Furthermore, when testing with renewables, you may want to test weather conditions that happen only every few years. With PowerHill, you can include wind simulators, gearboxes, and emulate both normal and extreme weather conditions. Similarly, if you're developing an electric powertrain, you complete a hardware prototype, and while the electric equipment and its controls are ready for testing, the battery pack and the electric motor may not be ready. Your interfaces could be 800 volts DC for the battery pack and 3-phase for the electric motor. The ideal scenario would be to perform endurance and performance tests under typical and extreme driving conditions, including battery voltage fluctuation, aggressive driving cycles, motor coil damage, overvoltages, among others. While the battery packs are not available, you can reproduce their dynamic behavior with a battery pack emulation and do it safely in a laboratory test environment. You can also test using motor emulation for typical and fault conditions, and even include driving simulators to consider different driving scenarios. Another relevant power converter for vehicle electrification is a high voltage DC fast charger. How do you develop it with different charging standards, vehicles, and grid conditions? In this case, we have a three-phase grid on one side of the converter and different DC charging voltages and standards on the vehicle side. How to test for weak grids, faults, or even cases when you can provide grid support back to the grid. With PowerHill, you can use grid emulation to test various grid types and also emulate different types of battery packs, while the availability of automotive and grid protocols could help where different charging standards are needed and also for different battery conditions. And you can even include multi-physics simulations via real-time testing to test the interactions with other components. And we could say the same for the more electric aircraft, where failure of a power converter could be life-threatening. Here we want to thoroughly test charging and flight conditions, and grid and battery emulation could support testing the battery pack and the electric propulsion, and also to provide emulation of physical components like resolvers or temperature sensors. Or when testing relays protecting the grid, systems whose failure could lead to severe damage to the electrical infrastructure, we could carry out low-level tests at extra low voltages in some cases, but testing the complete relay for different grid conditions requires including its current transformers, voltage transducer, and other sensors. Proper testing would require the reproduction of fault currents and voltages for different grid types. Grid and transmission line emulation in a laboratory setting can support the decommissioning, while test automation can be used for validation and verification of all protective functions. We have seen some of the challenges faced while testing electrical equipment, together with some of the benefits provided by power hardware in the loop testing, where the emulation of electrical systems and multi-physics real-time simulations can support reduced development cost and time. Now that we have seen how PowerHill can be used for testing electrical equipment, let me try to explain what it is. Let's say that you're developing a grid-connected energy storage solution that, together with some renewable energy sources, it will be providing power to the electric grid. As the equipment is part of an electric grid, its operation will be affected by other energy sources, the local utility grid, and the interconnection to the rest of the electric grid. The equipment will sometimes generate power while discharging and sometimes consume power while charging. One accepted testing methodology is power hardware in the loop. We will first isolate the electrical equipment that we want to test from the rest of the electric grid. We call the electrical equipment EUT, that stands for Equipment Under Test, and the rest of the electric grid is referred to as ROS, that stands for Rest of System. The rest of the system would be represented by an accurate simulation that can provide a realistic representation of the electric grid. For example, the electric grid can be modeled with Simulink and Simscape Electrical. It is then easy to combine with Simulink models and Simscape multi-physics simulation to include mechanical effects like inertia or gear transmissions, fluid dynamics for hydraulic systems, or other relevant environmental effects. So now we have the actual hardware or equipment under test on one side and the electrical simulation on the other. We're going to use an interface algorithm to partition the electric grid in the desktop simulation model. This interface algorithm is a mathematical tool that we'll use to partition the electric power network, with one part being simulated and the other part being the real electrical equipment. We use a properly rated power amplifier to connect to the real hardware. By linking a power amplifier to the interface algorithm in real time, we can maintain roughly the same instantaneous power at the connection point with the electrical equipment, both in the simulation and in the real hardware. The link between the power amplifier and the interface algorithm is critical and should be very fast, at least as fast as the grid dynamics that we want to evaluate. Therefore, we need to use a low latency real-time hardware. We add I/O blocks in the simulation to link to the I/O modules that are in the real-time hardware and thus provide set points to the power amplifier at every simulation sample time. While at the same time, acquiring all the available sensor measurements to be used in the simulation. A high-fidelity model built with Simulink or Simscape Electrical can execute every few microseconds and at every sample time then respond to the measured changes of the equipment under test. So then we can say that power hardware in the loop is a technique in which a piece of electrical equipment is incorporated into an electrical simulation by using an electric power interface. And what is the difference with hardware in the loop? Like my colleague Gernot, you may be more familiar with this term than with power hardware in the loop. So power hardware in the loop, it is specific for testing electrical equipment with electrical power. If we go back to our basic diagram for power hill, power transfer is maintained both in the simulation between the interface algorithm and the rest of the system, and in the real hardware between the equipment under test and the power amplifier. For hardware in the loop, there is no such electric power transfer, so there is no need for an interface algorithm or a power amplifier. For hardware in the loop, the electrical equipment is part of the simulation, and we typically interface to its embedded controller via extra low voltage signals, typically below 50 volts. This embedded controller may be a PLC, an electric control unit or ECU, an FPGA, a system on chip device, among others. These may include analog or digital signals as well as different communication protocols. Now that we have seen the basic components of the Power Hill test bench, we'll provide more details of each component in the remaining sections of this webinar. There will be an outline guide on the right-hand side of the slides for your reference. We'll start with the real-time hardware and its I/O interfaces, followed by more information on power amplifiers, and then the discussion of the requirements of an electrical simulation. Finally, we'll put everything together in a demo with a grid-tied inverter as an equipment under test. Let's briefly go through the Power Hill components, starting with the real-time hardware. Real-time hardware is not only used for Power Hill, but it is used at different stages of the development of electrical systems. This timeline represents a model-based design path without iterations that goes from the design and hardware implementation to the final deployment as part of the electric grid, electric vehicle, or another electric system. With model-based design and real-time testing, you can go from early designs through all the iterations and test cases via a flexible and powerful workflow combining software and hardware. It involves controls testing using rapid control prototyping, and once we have an embedded controller or electrical equipment ready for testing, it also involves using a virtual plant for validation and verification like with power hardware in the loop. This includes the emulation of other components like resolvers, relays, or battery cells. So electrical system development strongly benefits from real-time testing. The real-time simulation and testing platform by Speedcode and MathWorks combines a desktop simulation environment for multi-physics modeling, control design, and test automation, together with a real-time simulation and testing environment that lets you connect with real equipment or embedded controllers. Together, they provide a unified platform, benefits from a plug-and-play real-time solution that avoids interoperability issues, experience the unity of simulation and testing with real-time target hardware, all directly from MATLAB and Simulink. The integrated solution is composed of two main components. The first one is Simulink Real-Time, the solution for real-time simulation and testing from within MATLAB and Simulink. It comes with several host capabilities that allow you to create, control, and monitor your real-time applications, and serves as your real-time operating system. The second component is a powerful and scalable Speedcode real-time hardware equipped with I/O connectivity, communication protocols, and plant emulation capabilities. The real-time application created from your Simulink model runs on it together with the Simulink real-time operating system. Once your models are ready, you go from desktop to real-time simulation and testing with a click of a button, while you continue to tune parameters, provide set points, and measure from within Simulink. Choosing real-time hardware for PowerHill consists of choosing a real-time target machine, I/O modules, and sometimes also FPGAs and plant emulation capabilities. Target machines include multi-core CPUs that will typically handle the electrical simulation as well as some onboard connectivity like serial communication, EtherCAT, XCP, or DMP3. The performance real-time target machine is the ideal choice due to its capacity to handle large electrical simulations. Then you select I/O modules for various I/O connectivity or communication protocols. FPGAs for high-fidelity power electronic simulations, high-speed I/O, or other high-end functionality. And you require component emulation capabilities like resolver, encoder, or battery cell emulation. For I/O modules, there is a wide range of I/O connectivity and communication protocols supported off the shelf. One important choice would be the use of high-speed analog interfaces for the power amplifier, ideally low latency I/O modules with several channels, as you'll typically need several measurements. And digital interfaces may also be required to control the power amplifier or to handle electrical protection circuits. While there is a wide range of protocols supported, for power hill you may typically need DNP3 or IC61850 to interface with other elements of the electric grid or a SCADA system, Aurora to interface power amplifiers with very high bandwidths via fiber optic, or an industrial communication protocol like Modbus or Profinet to interface with power amplifiers and ancillary equipment. Speedcode also offers fully customized rack systems for your power hill test bench. The racks can be customized to include other power components, and it's possible to integrate components like power amplifiers, digital signal processing, DC or AC power supplies, three-phase inverters, protection relays, among others. Now that we have covered real-time hardware, let us discuss power amplifiers and how to choose one. From the power hill diagram, the power amplifier provides a power link to the equipment under test that, thanks to its links to the interface algorithm, it keeps roughly the same instantaneous power as in the simulation. Key considerations for selecting power amplifiers are: first, the electrical specifications. As they connect to the electrical equipment under test, they should provide at least the required power and voltage levels. Second, the source and sink capabilities to be able to act as a load and as a power source. This is typically referred to as 2 or 4 quadrant operation. You'll typically require only 2 quadrants for sourcing and sinking DC, as voltages will not change sign. But you'll need 4 quadrants for sourcing and sinking AC power. Bandwidth is key. For simple AC grid emulations, bandwidths of 1 to 5 kHz may be enough, but bandwidths of 5 kHz or higher are preferred for harmonic, fault transients, transformer saturation, and motor emulation. An important feature is for power amplifiers to track either voltage or current setpoints. This will be relevant when choosing your interface algorithm. Voltage tracking is typically used for grid emulation, while current tracking can be used for emulating a load, such as a motor. And finally, the interface with the real-time hardware. Analog signals can be used but require noise filtering and ideally also galvanic isolation. We can also use fiber optic links with high-speed communication protocols like Aurora. We need these interfaces as real-time simulators use much lower voltages than electrical equipment. Power amplifiers would be then controlled by analog signals with a typical range of plus minus 10 volts, or a high-speed fiber optic link. Sensors for voltage and current are meant to provide outputs at extra low voltage for real-time hardware. Key considerations include electric isolation and a high bandwidth, at least as high as the simulation closed-loop bandwidth. Voltage and current transducers would typically require to output voltages in the range of plus minus 10 volts to interface with the real-time hardware, and they can also be available with the fiber optic link. Power amplifiers also tend to include sensor signals with an interface to the real-time hardware. Speedcode works with various power amplifier manufacturers as they tend to have different electrical ratings, bandwidths, sensor interfaces, and emulation capabilities. To simplify setting up a power hill test bench, Speedcode offers turnkey interfaces with a few manufacturers. For example, we offer a custom analog interface to Synergia power amplifiers, or even a fully configurable power amplifier with a Simulink-based controller. With Exton Power, we offer a fiber optic interface based on the Aurora protocol and a Simulink-based electric motor emulator. For selecting power amplifiers, you could start considering their electrical ratings. For example, for grid emulation or battery pack emulation, you could use power amplifiers from Synergia or Spheria when working up to 10 kilowatts and 540 volts of line-to-line voltage. You could also use Exton Power or Regatron for power amplifiers up to 160 kVA. You can even use Exton Power amplifiers up to 2 megawatts. On the other end, you could use Turner for single-phase power amplifiers up to 1 kW. For electric motor emulation, you could use our joint solution with Exton Power up to 50 kilowatts, and either Exton Power or the e-motor emulator from D&V Electronics up to the megawatts range. Speedcode offers fully customized rack systems for your Power Hill test bench, including working setups for grid emulation, motor emulation, and battery pack or cell emulation. Now that we have seen the hardware requirements for a Power Hill test bench, let us discuss the software components. Gernot, how can we combine the simulation of an electrical system with actual electrical equipment?
Sure, Carlos. On this slide, we can see a model of a solar panel or a wind turbine that uses an inverter for the connection to the grid. Now, if we want to test a real inverter, which is, for example, under development, it would be very risky to do that against the real grid, since it might not have been tested thoroughly yet. Well, we can split up the model just next to the inverter on the three-phase power lines, and we can run the grid as a real-time simulation on a SpeedCode real-time machine. That's what you can see on the left side. On the right side, we have the real power hardware, the inverter. Since the splitting happened on a three-phase power line, we will need to apply a power source here to feed the inverter. Therefore, an amplifier is used. The amplifier is driven by signals coming from the real-time grid simulation. In such a test setup with two electrical systems, the grid simulation on the left and the inverter on the right, signals also must be exchanged in the opposite direction. Therefore, a sensor signal is typically used that closes the loop. Here, an interface algorithm converts the three-phase electrical connections from the grid simulation into bidirectional signals. Important here is to understand that in case of power hardware in the loop, the interface of the unit under test is a power interface. Unlike in the traditional Hill case, the network is not split up at the data interface. So what are the benefits of SimScape and the add-on product SimScape Electrical? SimScape Electrical is coming with a comprehensive block library. There are different power sources like PV panels, wind turbines, batteries, and fuel cells, but also components used for transmission line modeling, transformers, various electrical machines, semiconductors, and converters. Depending on the required fidelity level, you can select between simple models that can be used for energy flow simulations or very detailed models that include thermal effects or motor models that are based on FEM data and much more. So the base product SimScape already supports several physical domains, like the electrical domain, but also mechanical, magnetic, and thermal domains that all can play a certain role for the modeling of electrical power systems. There are also additional domains, mainly for thermodynamic system modeling, like hydraulic domain, thermal-liquid domain, two-phase fluid domain, and the gas and moist air domains. Some of them can be used for active cooling systems. Besides SimScape Electrical as the main product for power system simulation, also SimScape Driveline for mechanical powertrains, SimScape Multibody for 3D mechanical systems, and SimScape Fluids for all fluid transport simulations like used in cooling, deliver a wide set of blocks on various levels of detail. Another interesting point is that it is possible to author your own custom components with SimScape language. So far to the physical modeling tools themselves. The main benefit comes from the tight integration of all those modeling tools within the model-based design workflow. Thus, you can model multi-domain physical systems with controllers, generate code out of the physical models for hill or power hill testing, and analyze and design controllers based on electrical system models. Also out-of-the-box multi-core support for many workflow scenarios like parameter sweeps and optimization is possible. A last topic I want to mention here is the capability to build bigger models automatically by using MATLAB scripts. This especially plays a role if a model contains a lot of repeating structures, like the cells within a battery model or transmission or distribution line sources and loads within an electrical grid model. So far, we have seen how SimScape Electrical is used for building up the real-time model of our test setup. What's still missing in our consideration is the interface algorithm that allows a signal-based connection of the power amplifier and the current sensor feedback with the electrical circuit. Introducing these bidirectional signal-based connections, as we have seen before, will require splitting of electrical circuits. The circuits are described with differential algebraic equation. Normally, Simscape solves the complete circuit equations iteratively per time step. But if we split up the electrical network, this will not be possible any longer. We will get the voltage Vload 1 as an output signal that can be transferred to the other partial network. Now the same calculation starts at the right side. As a result, we get the current Iload 2, which is fed back to the left side again. In our final setup, the left side can represent a real-time model of a grid, for example. The right side can be another real-time simulation model on a different core or a physical power device. There are different methods now to implement the signal-based coupling of two partial networks. All of them must take into account that exchanged values are from the previous simulation time step. I just want to show you the most common one, which is called ideal transformer model. So let's start with two partial networks. As shown before, voltage is measured on the left side and transferred to the right. The current is measured on the right side and transferred in opposite direction. To solve the algebraic loop problem with the signal values from previous time steps, we must add so-called unit delays to the coupling signals. It is important to make sure that such a coupled system still is stable and accurate enough for your simulation. For the ideal transformer model, the following criteria have to be fulfilled for stability. The ratio of the magnitude values of the source impedance and the load impedance, shown here, must be lower than 1 for the coupling as shown with the voltage transfer from the left to right. If the ratio is higher than 1, then the coupling will cause instability. To avoid that, the coupling mechanism must be flipped so that the current goes from left to right and voltage in the opposite direction. Here you can see the ideal transformer model. In the top section, you see the reference model of the electrical circuit which is not split up. So you see here a source impedance and a load impedance, and the values for the impedances are predefined in a callback here. Source impedance is 1 ohm and the load impedance is 50 ohms. So we fulfill the requirements here for voltage transfer from left to right. In the lower section, you see the split up model. And we couple that with the lines here. So now let's simulate the model just to see the stability and the accuracy of the ideal transformer model. If we zoom in here, we can see a one-step delay and a small overshoot, but it's stable. Now, if we change the values here of the impedances, and we use, for example, 2 ohms here on the load side, run the simulation again. Now I can see the dynamics has changed. It's still stable, but we have an oscillation here. If we now go for a resistance value lower than 1 ohm on the load side, and we run the simulation, you will see that the system is unstable. Yeah, we cannot use it like this. So in that case, we would have to change the direction of the coupling network. Now, if we want to use a power amplifier instead of splitting the electrical network, a similar concept is used. Once again, we have to use an interface where we convert circuit-based electrical states into signals. But now the forward signal is used to drive the power amplifier, and the backward signal is a measurement of the real current. In the power hardware setup, coming from a current sensor. Here in the power hill, the unit under test is driven by power output from the amplifier. The challenge here is that the power amplifier never is ideal. It will also have delays and a finite bandwidth that influences the stability here, quite similarly like in the case before, where we coupled two real-time simulation models. Nevertheless, frequency analysis methods like those from Control System Toolbox can be used to find a stable solution depending on your specific setup. Additionally, I want to mention that this approach with the power amplifier does not only work for passive loads, but also for active loads. This is only one example for building up the interface algorithm. As mentioned before, it will be worth to test also other approaches that can be found in publications or PhDs. All have their specific advantages and disadvantages, depending on your specific setup.
Many thanks, Gernot, especially for illustrating the complex interface algorithm concept with a simple example. Now, let us move to the Power Hill demo. We'll be using Power Hill testing to commission a grid-tied inverter rated at 15 kVA with a two-level three-phase inverter topology and including an LCL output filter. It is connected to a 60 kVA power amplifier from Synergia, specifically an E plus G plus EL capable of syncing and sourcing both alternating and direct currents. It can also act as a voltage source or as a current source, where G stands for grid emulator and EL stands for electric load. Therefore, it operates as a four-quadrant power amplifier. The power amplifiers from Synergia include a set of voltage and current sensors for each phase that may be accessed via analog channels. We'll use these sensors for this demo. The current and voltage set points are provided also via analog signals. The real-time simulation is handled by a performance real-time target machine with high-speed analog interfaces. And finally, a Simulink model composed of the rest of the electric system and an interface algorithm. We also connected a Fluke 435 power analyzer in between the power amplifier and the grid-tied inverter. It is like an oscilloscope for three-phase electric power to measure instantaneous voltage or current, visualize phasors for checking three-phase alignment, among other features. As a side note on our setup, you'll see another Speedcode real-time hardware next to the equipment under test. This performance real-time target machine is not part of the PowerHill setup, but acting as a controller of the equipment under test. As in a typical power electronics development phase, it is controlling the gate drives of the grid-tied inverter that are being used to test different control methodologies. Let's start with the Simulink model of the electrical system without the equipment under test, also known as rest of system. In the Simulink model, we have the electrical model of the rest of the system on the left, the interface algorithm in the middle, and the analog interfaces to the power amplifier on the right. We've added also an overvoltage protection in case there is an unstable behavior in the model. The CPU-based simulation is running with a sample time of 50 microseconds or 20 kHz. It is a good practice to test your interface algorithm connecting to the rest of the system with the equipment of the test also in desktop simulation prior to PowerHill testing. For that reason, we use variant models to go between desktop simulation and PowerHill testing. In the desktop simulation, we have a representation of the equipment under test. For PowerHill, we just need analog input and output interfaces to the power amplifier. As we have already tested stability in desktop simulation, let's now run the model. We deploy the model to the real-time computer on the right. It is running the rest of system in real time and providing references to the power amplifier. We have set an 80 volt RMS phase voltage for the test. Once we enable the power amplifier, we can see the three-phase voltages on the power analyzer. If we switch modes to the phasor mode, we can also see the phase vectors with all being aligned at 120 degrees. We can see this voltage also on the front panel of the Synergia power amplifier. With our simulation, we can easily start or stop the operation of the power amplifier as we do now. With the simulation data inspector, we can see the measured signals as well as several signals in our model. Now that the power hill setup is operational, we'll go to the control panel of the grid-tied inverter and carry out the grid synchronization and then the current controller testing. Notice that we had a control panel for 3 converters and we're using the converter number 3. The DC bus is already enabled and charged. Before closing the contactors, we let the phase lock loop synchronize to the grid provided by the power amplifier. Then we'll close the contactors and connect to the virtual grid. Failure to synchronize correctly would result in large currents potentially damaging the equipment. We synchronize and we gradually increase the current. This is a very powerful approach as we can enable the converter in different grid topologies, check the grid stability as well as the grid code compliance like fault right-through testing, and test different faults of the electrical equipment and the controller. We're now at the end of this webinar, and there are 3 key concepts that we would like for you to take with you. First, that you can use Simulink with power hardware in the loop testing to de-risk the integration of power systems and power electronics equipment. Second, that you can test the integration of both DC or AC power grid components with a large and detailed grid simulation. This simulation can be based on Simscape electrical models and thus enable a straightforward transition from desktop simulation to testing with real hardware. And third, that you can thoroughly test power equipment like inverters, protection relays, and battery chargers using power hill testing and speed code hardware. And you can debug, test, and automate from within Simulink. Thanks for your attention.
You want to learn more about real-time controls testing? Then find additional content linked here.